Hello, I'm Dr. Maurice Dupre, and in this section we're going to discuss volumes by cylindrical shells. Let's see how, when we take a region and revolve it about an axis to generate a solid of revolution, we can get a formula for that volume thinking in terms of cylindrical shells. Shell formula for revolution about a vertical line. The volume of the solid generated by revolving the region between the x-axis and the graph of a continuous function y equal f of x, where f of x is greater than or equal to 0, and the line L, which is less than or equal to a, and a is less than or equal to x is less than or equal to b, is the restriction on the region we want to rotate, and about a vertical line x equal L is. So v is equal to the definite integral from a to b, 2 pi times the shell radius multiplied by the shell height dx. So here in this little picture, here's the x-axis. I've drawn x here right on the x-axis and y up here for the y-axis. And here's the graph of our function f. And so here are our two limits. And basically what we want to do is take this region under the graph of f and revolve it about this vertical line L. Notice in this case what I've got is L is to the left of the region that I want to revolve. And notice when I do that, it sweeps out, generating a solid of revolution. And in particular, if I take a vertical line at a specific value of x here, that vertical line under the revolution sweeps out a little cylinder. We think of it as a cylindrical shell if we think of it as having a certain very small thickness dx. And so consequently, what would be the volume of this little thin shell? Well, it would be the surface area of the shell, which is 2 pi times the shell radius, giving the circumference of the top, multiplied by the shell height. That would give the area of the shell. And so if I multiply by a little tiny thickness dx, then that product is a little bit of volume, which we can think of as dv. In other words, I can think of this volume here as being the integral. I'll write a to b dv here, but you have to understand that these limits are not in terms of the volume v. What I'm thinking of is this little dv right here is this bit, which is given by the entire product, 2 pi shell radius, shell height dx. And so consequently, when we look at a problem like this, it's best to work it out by looking at the geometry of the problem, work out the shell radius, the shell height, and notice in this case the shell radius is going to depend on x. And so consequently the dx is related to the shell radius. So keep that in mind. All right, now let's work a problem where we compute the volume of a solid of revolution by the method of cylindrical shells. Here we have the picture of the region under the curve y equals square root of x squared plus 1 for x between 0 and square root 3. Here's the vertical line x equals square root 3, which is the right-hand edge of our region. And we want to revolve this about the y-axis. So if here's a typical x, notice as we revolve around the y-axis, this vertical line above x, going from the axis all the way up to the curve, is going to sweep out a cylindrical shell. And of course, the shell radius is simply x. And what's the shell height? Well, that's y. And so the little bit of volume dv generated by that cylindrical shell is 2 pi times the radius x multiplied by the height y times dx, which is a little slight thickening of the shell radius. In other words, the thickness of the shell comes from a thickening at x here. And so that generates a little bit of volume. So in particular, that tells us in terms of our equation for the curve, dv is 2 pi x times the square root of x squared plus 1 dx. And that we want to integrate from 0 to square root of 3. So there's our problem, and let's compute the integral. So we want to compute the definite integral 0 to square root 3 2 pi x square root of x squared plus 1 dx. Now to do that, we immediately spot that we've got something other than just x inside the radical, and so we'd like to do a substitution. We'd like to substitute u equals x squared plus 1. If we do that, du is 2x dx. Here's our 2, here's our x, there's the dx, and so v equals definite integral. The pi can come out, and the 2x dx just becomes the du, and so the only thing we'll have inside is square root u. But what are our new limits? When x is 0, u is 0 squared plus 1, or simply 1. When x is square root 3, the square root of 3 squared is 3 plus 1 is 4. So we end up simply with the v equals pi times the definite integral from 1 to 4 of square root u du. Well, that's anti-differentiating u to the 1/2 power. That leads to u to the 3/2. So we have u to the 3/2 divided by 3/2 to be evaluated from 1 to 4. Of course, a 3/2 down in the denominator is the same as a 2/3, and so we have 2 pi divided by 3 u to the 3/2 to be evaluated from 1 to 4. Well, let's put in the upper limit. When I do that, 4 to the 3/2 means square root of 4 cubed. Well, square root of 4 is 2, and 2 cubed is 8. Putting in 1 just gives us 1, so we have 8 minus 1, which is 7, and 7 times 2 is 14, so we have 14 pi over 3 as the volume for the region, the solid of revolution obtained by revolving this region about the y-axis. So the final result is v equals 14 pi divided by 3. Well, sometimes when we revolve a region to generate a solid of revolution, it's convenient to revolve around a horizontal axis instead of a vertical axis, and consequently it's useful to see how the formula goes in this situation. So when we revolve about a horizontal line L, the shell formula is going to become v equals definite integral from a to b of 2 pi shell radius times shell height again, but this time it's dy that we're going to multiply by, and the reason is since our line is horizontal, so our typical cylinder, you see, drawn here, its shell radius is going to depend on the y coordinate, and consequently its thickening is going to be in the y direction dy. So in effect, our dv is 2 pi shell radius, shell height dy. You think of all of this quantity as equal to our little bit of volume. All right, let's look at an application of the shell formula for revolving around a horizontal axis. Here in this problem, I've got the region between the horizontal line y equals square root 2 and the curve x equal y squared. So here's the region, and I want to revolve it about the x-axis. So that means my typical cylindrical shells are going to have be laying over on their sides, and so here's the edge of a typical one at height y, and so when this revolves around the x-axis, it's going to generate, you see, a cylinder like this, big cylinder in this case with that height in this picture, and Consequently, we see that the shell radius is y. So the shell radius equals y, and the shell height, because the shell is laying on its side, the height is actually this distance. Well, notice the shell height is the x coordinate of that point. So now the shell height equals x. And so our dv is 2 pi shell radius y times the shell height x. And what do we multiply by? You look at the shell radius expression. It's dy that we would multiply by. Now, here in this expression, x, we look at our curve here, which is relating x to y. We see x is y squared. So in effect, we're going to integrate 2 pi y times y squared dy, and now we merely have to look at our limits on y. What's the variation of y? Y goes from 0 up to square root 2. So there's our volume in this case. V equals the definite integral from 0 to square root 2 of 2 pi y times y squared dy. So clearly then, all I have to do is integrate 0 to square root 2 pi y cubed, which is y times y squared dy. Well, that's an easy one to do. You can take out the 2 pi. Antiderivative of y cubed is y to the 4th over 4. That's to be evaluated between 0 and square root 2. Of course, we can cancel 2's here, 2 with 4. Cancel those, leaves a 2 down in the denominator. And square root of 2 to the 4th power is the same as 2 squared, which is 4. So we have pi times 4 over 2, which is 2 pi. Now let's look at this again. Here's our original picture that I looked at. dv is 2 pi y times x dy. We could have turned this into an integration against x if we wanted to. The reason is that we can relate the dy to the dx. If we do, remember x is y squared, so dx is 2y dy. Here's a y, here's a 2, here's a y, so we get pi x dx. So we could also say dv is pi x dx. And what would be our range of integration now? Well, notice that dv equal pi x dx is a very simple thing to integrate. So what is our range of x? Well, notice in the x direction, we're going from 0 all the way to 2. So if I did it this way, the integral would be even simpler. V equals the integral from 0 to 2 pi x dx. Let's calculate again. Take out the pi, anti-differentiate the x. That's x squared over 2. Evaluated from 0 to 2, we get pi times 2 squared over 2, which is clearly 2 pi. So this shows you that in general there's more than one way to go with these, even though you're integrating, in this case for revolving around a horizontal axis, we in effect turn the integral into an integral against x. Well, sometimes the region we want to revolve is described by several curves forming the boundary. Let's look to see how we can still get the volume. Let's revolve about the y-axis, the region y equal x squared, y equal 2 minus x equals 0 for x greater than or equal to 0. That is, here x to the right of the y-axis being x equals 0. And here's our x-axis coming down here to the right. Here's the curve, which is a straight line, y equal 2 minus x. and here's our bit of the parabola y equal x squared. And so they enclose this region here, parabolic bottom and a kind of an angled straight line top. And that we want to revolve about the y-axis, and so for a typical x, we've got this vertical line strip here, which will generate for us a vertical cylinder when it's revolved. Notice its base is not on the x-axis, so the shell height in this case is not simply this upper limit here, y along this line. It's the difference between the value of y here and the value of y here. In other words, the shell height, we abbreviate that SH period, is equal to 2 minus x minus the y value here, which is along the parabola x squared. So that's our shell height. And of course our shell radius, which I'll denote by S period R period, is just the x. And so consequently in this case, our dV is equal to 2 pi shell radius x multiplied by the shell height, which now has this more complicated formula, effectively 2 minus x squared. So what are our limits of integration going to be? Well, our region starts out at x equals 0, and the farthest right it goes is x equals 1. You can see this point right here, where the parabola crosses the line, is the farthest right in this region. So consequently, all we have to do is integrate our dV from 0 to 1 against x. Let's do that now. So our formula then would be v equals the definite integral from 0 to 1 of 2 pi x times the quantity 2 minus x squared dx. And so the first thing to do is multiply the x through, and we'll take out the 2 pi. And so we get 2 pi integral from 0 to 1, 2x minus x squared minus x cubed dx. So 2 pi times the antiderivative 2x is x squared. Antiderivative of x squared is x cubed over 3 minus the antiderivative of x cubed, which is x to the 4th over 4. And that's to be evaluated from 0 to 1. So we get 2 pi times 1 minus a third minus a fourth. And of course, that's easily seen to be simply 2 pi times 5/12. In effect, a third plus a fourth is 7/12. 12/12 minus 7/12 is 5/12. Well, of course, we could cancel the 2 with the 12, and that would be 5 pi over 6 is the final answer for the volume when you revolve that region about the y-axis. Let's look at a problem where we calculate the volume of a solid of revolution obtained by revolving a region about the x-axis. Here, I want to revolve about the x-axis the region between the curves y equal absolute value x and y equals 1. Well, why don't you pause the video and try this one yourself and then see how I work it. Okay, so what we need is a picture of the region that we're talking about, so we begin by graphing those two. Well, we all know that the graph of y equal absolute value x is a V-shaped. It's just the two lines y equal x and y equal negative x, the parts above the horizontal axis. On the other hand, y equal 1 is just a straight horizontal line. So the region we're talking about is this region in here. That's what's between those two. And so we're revolving around the x-axis, remember, and so our cylinders will have their axes of symmetry lying along the x-axis. So typically for a height y here on the y-axis. The cylinder stretches from back here at a given value of y. Well, notice this point right here has coordinates x and y are the same. So this is y comma y, and this point back here is y comma negative y comma y, and we're revolving around the x-axis, so our cylinder looks like this. So our shell height, this is the x-coordinate of the point, is obviously 2x. Our shell radius, of course, is y, and so dv is 2 pi y times 2x, but remember, it's the shell radius that we integrate against, so we don't have a dx here, we have a dy. So now we have a y and an x. What we would like to do is put everything in terms of y. Well, for a given x right here, x and y are the same along this line, y equals x. So we could just replace that x by a y. So that would be dv equals 2 pi y 2y dy. Alternately, we could notice that because along this line y equals x in effect when x is positive and y is positive, that therefore the dy and the dx are the same. So consequently, we could write it just in terms of x or y, it doesn't matter. V is equal to the integral from 0 to 1, 2 pi y, which is absolute x, times 2x dy, and we can simply replace that dy by a dx here. And so we get the integral from 0 to 1, 2 pi absolute x, 2x dx. Well, of course, in the range 0 to 1, absolute x is just x, so that's simply a factor of x. We've got 2 times 2 is 4 pi, integral from 0 to 1, x squared dx. Well, the antiderivative of x squared is x cubed over 3, so we have 4 pi over 3x cubed evaluated from 0 to 1, and of course the evaluation of x cubed from 0 to 1 is just 1, and so this is 4 pi divided by 3 is the final answer for this volume. Now let's find the volume of a solid of revolution where the region revolved has a boundary given by curves where it's not quite obvious where they intersect, so we'll have to look carefully to see what the region is. Here I want to revolve about the x-axis the region described by y equals square root x, y equals 0, and y equal x minus 2. Notice if I draw a quick sketch here, y equals square root x is a parabola on its side, the upper half opening to the right like this, and y equal x minus 2 is a line of slope 1 which goes through the vertical axis at height -2, 2 units down, so it's coming through like this. And so what we're going to have to do is find this point where the line intersects the parabola. To do that, we begin by looking at the equation square root x equals x minus 2. That's how we'll find that point. Notice our other boundary line is y equals 0, so the region we're talking about here is this little funny shaped region that's going straight along there and then coming along at slope 1 up here, and then it's got this parabolic top here. And so to find this point, we need to find square root x equal x minus 2 solution. So to begin, you square both sides of that equation, you get x equal x minus 2 quantity squared. And so consequently, that gives us the equation x equals x squared minus 4x plus 4, or bringing this x over to the other side, we get the equation x squared minus 5x plus 4 equals 0. Well, that's easy to factor. Notice it's just x minus 1 times x minus 4. So consequently, coming over to another sheet here, we have x minus 1 times x minus 4 equals 0 as a factorization of the x squared minus 5x plus 4. And so that gives us the solutions x equal 1 and x equal 4. Now let's look at our original picture. What do those solutions mean? Notice when we squared both sides of the equation here, in effect we're dealing with the whole parabola. And this parabola, the curve x equals y squared would come on down through here. And so here is the solution where they cross, which is x equal 1. That's outside the region we're interested in. It's the x equal 4 right here that's important to us. And so this is the point here, 4 comma square root 4, 4 comma 2. So the coordinates of this point of intersection are 4 comma 2. The line crosses the x-axis here at x equal 2, and here the origin is our other vertex of this region. So this whole region is to be revolved about the x-axis. Okay, so now let's look and see what we would get for our dv. So drawing the picture again, roughly, here's our line. Typical horizontal cylinder, now remember we're revolving around the x-axis, so our axis of symmetry for these cylinders is going to be the x-axis. So our shell radius is equal to y, and our shell height is the difference of the x-coordinate here and the x-coordinate here. In terms of y, the line y equal x minus 2 is the same thing as saying x equals y plus 2. So we could say the x coordinate of that point in terms of y is y plus 2. What about the x coordinate of this point? This is y equals square root x here. And so consequently, that's the curve, if I square both sides, x equal y squared. So here we have y squared as an x coordinate. Here I have y plus 2 as an x coordinate. And so the shell height is the difference of those, y plus 2 minus y squared. And so finally then, in this case, our dv is 2 pi y times the shell height, y plus 2 minus y squared dy. Remember, the dx or dy is determined by the shell radius. In this case, our shell radius depends on y, so we have a dy. Now, we're integrating against y. What are our limits of integration? Come back up here to this point. Remember, that's the point with coordinates 4 comma 2. Down here, we're at the origin 0 comma 0. So notice our total variation in y is from y equals 0 up to y equals 2. So we merely integrate dv from 0 to 2 in terms of y. Well, we've worked out our dv expression in terms of y, and we've realized that our range of integration is from y equals 0 to y equals 2. So now we can easily set this up and work out the integral, which gives the volume. So here's our integral. The volume v of our volume of revolution is integral from 0 to 2 of 2 pi y times the quantity y plus 2 minus y squared. Remember, y is the shell radius, and this is our shell height. Now, the first thing to do is multiply the y through, take out the 2 pi, so v is equal to 2 pi integral from 0 to 2, y times y is y squared, plus 2y minus y cubed. So the antiderivative 2 pi times the quantity y cubed over 3. Antiderivative of 2y with respect to y is y squared minus y to the fourth divided by 4. And of course, this is to be evaluated between limits 0 and 2, and so that means, since obviously putting in 0 gives nothing, we just substitute in y equals 2, and that gives the answer. So v equals 2 pi times 2 cubed is 8 divided by 3 plus 2 squared is 4 minus 2 to the fourth is 16 over 4, that's 4. And so we get, these cancel, 2 times 8 is 16 divided by 3 pi. So we have 16/3 pi as the final answer. All right, now we've worked several problems for revolving regions about axes. Generally, the axes that you'll have to deal with are either the x-axis or the y-axis. Occasionally, you have to deal with revolving around a line which is vertical and not the y-axis, or horizontal and not the x-axis. But in any case, remember, draw a picture. Then when you're revolving around a given axis, that tells you the side of the cylinder, a typical cylindrical shell, will be parallel to that axis of revolution. So draw it and draw yourself a little schematic cylinder, and then you can easily work out the shell radius and then the shell height. In that case, you're just integrating 2 pi shell radius times shell height times dx or dy, and the thing that determines whether it's dx or dy is to look at the shell radius. If the shell radius is in terms of x, then it's dx. If the shell radius is in terms of y, it's dy.